Okay, so this video again, you might want to pause, copy the circuit down. I need to put one more thing in the circuit here, that we've got the dot up here. So we have an ideal transformer here, and we are going to look at what the impedance is that we see here. So if you want to pause it to copy it down, great. Otherwise, I'm going to get just started here. So I have a plus minus V1 here labeled. I already labeled that because, remember, with the ideal transformers, we want to be able to use the equations V1 over N1 is equal to V2 over N2. And then we also want to be able to use the other equation that I1 N1 is equal to I2 N2. Because remember, there's four different configurations, but it's just easier to think of one configuration and just set up your problem so that it has that configuration. So the way we're going to set this up here is, well, I need to have my I1 entering the dot. I need the I2 to be leaving the dot. That's the wrong way then. I need it to be leaving the dot, I2. And then we have this voltage plus minus V2 because the positive goes on there. And if you don't set it up like this, these equations won't hold. The difference is, if you look online or in your book, the difference is that there's going to be negatives floating around in these equations. And that's why I just like say, well, remember one set of equations. You don't have to worry about negatives, and just always set it up like this so that you have the pluses for both V1 and V2 at the dot. I1 enters the dot. I2 leaves the dot. Alright, so we've got it set up now. Now we need to find the impedance. And you might say, I have no idea where to start. Well, this is where we have to go back to circuits 1. And remember, think of it as that you're saying finding the impedance here. You're trying to find the Thevenin impedance. But the idea here is there's no voltage source. So what you can do here is simply apply a test voltage source. And then ZAB would be the test voltage source divided by the current that's coming out of this. Now, of course, here we can see clearly that the current I test is just simply equal to I1. So no problem there. And then we can also clearly see that, what is this? Oh, the V-test. That V-test in this case is actually also equal to V1 because they're in parallel. Now, one thing to make life a little bit easier is, instead of just using V-test here, I'm going to actually put a value here. And it doesn't matter what value you use, but I'm just going to put 1 volt here. So then my ZAB is simply going to be 1 volt over, well, I1 or I test, because that's what it is. So we have to figure out what I1 is. Okay, well, we basically use these equations here. So we know here, well, for instance, we know that V test is equal to V1. So this gives me that V1 is equal to 1 volt. And now we're just going to do a lot of equation substitution here. It's actually, it looks like it should be a difficult problem, but it's not. I'm going to look at this equation here, because if I know what V1 is, I can figure out V2 easily. So I'd have that V1 over 25 is equal to V2 over 1. Right? Because that's just what I have here with my ratios. And so we get, then plugging this in, we simply get V2 is equal to 1 over 25 volts. It's 1/25 of a volt. Alright, so I'm going to scroll back up here. I know I keep scrolling back and forth here. I apologize for that. And now what we're going to do here is, well, wait, I know this voltage, and I know this voltage has to equal the voltage across these two components here. I'm going to basically just write a loop and solve for I2. So what I'm going to do here is I'm going to go ahead and just follow my current here. And so my current I2 would be minus J 14.4 ohms times I2 plus 4 ohms times I2. And then let's look at what side am I coming into. I'm coming into the negative side. So minus V2, and that's equal to 0. But then, let's think about this. I know what V2 is, so I wind up with 4 minus J 14.4 times I2 is equal to V2, and I'll just erase the V2 because that's equal to 1 over 25. So then we have that I2 is equal to 1 over 25 times 4 minus J, hello, can't do arithmetic here, 1 over 25 times 1 over 4 minus J 14.4. Because I obviously would divide both sides. Now you could compute that number out. I'm just going to leave it for now because I'm just still doing some equation substitution. Because remember, my goal is to find I1, because then ZAB is just 1 divided by I1. But then I'll switch colors again here because I like to switch colors. We have another equation that I1 N1 is equal to I2 N2. Okay, well, now I know what I2 is, so I'm simply going to say, okay, well, I've got I1 times 25 is equal to I2 times 1. And substitute in I1 times 25 is equal to 1 over 25 times 1 over 4 minus J 14.4. Well, solving this then just gets me I1 is equal to 1 over 25 squared times 1 over 4 minus J 14.4. And now if I do that computation, finally, because that's what I'm looking for is I1, I wind up with 28.65 plus J 103.2 microamps. Now if you have this in your calculator, remember we're just getting that my ZAB is simply just 1 over I1, so you could literally just do the reciprocal of your answer. You don't have to like actually do this computation, you know, like typing it in like this. I mean, you have to do the computation, but you don't have to literally type it in. You can just use your calculator and do the reciprocal of this. And if I do the reciprocal, I get 2.5 minus J9 kiloohms. So that means that this transformer is going to see this ZAB, you know, the equivalent circuit for it would be a resistor with a capacitor minus J 9K ohm and 2.5 K ohm. Now, you might say, why would I do that? Because really, if you're talking about a transformer, I've suddenly lost all of the useful information as far as like, well, I don't know if this transformer is step down, step up. I mean, I do know just looking at the turn ratio, whether it's a step down or step up. I mean, you can just look at that back at the voltage equation here. V1 over N1 is equal to V2 over N2, and N2 is 1, so it's a step down because you're dividing by 25. Whatever your V1 is getting divided by 25. So it's clearly a step down transformer. But my point being here is, why would you want to know this? Well, we're going to be talking about something, actually the next couple videos is where we'll begin it, is we'll be talking about now power in steady state. And eventually we'll want to talk about maximum average power transfer. And so what we can see, based off the load that's attached to this transformer, this ideal transformer, we have basically a capacitive load. So the source is going to see a capacitive load effect. And what we're going to want to do if you want maximum power transfers, you're actually going to need to kind of cancel out this capacitive load effect. And you do that by basically putting an inductor in series of the same value. And we'll cover that obviously in more detail, but there is a reason for wanting this as opposed to, hey, here's a problem to do. You know, there is a reason why we'd want this. Alright,